Hello, my dear children. Welcome back to our session. I know, the exams are coming very close, and the tension is building up. But you know what I always say, when I am here, there is no need to fear. Today, we're going to tackle the chapter on atoms, and I promise you, by the end of this, you will find it to be one of the easiest, most scoring chapters. Are you ready? Let's begin.
So our story starts like a great detective mystery. The question is, what is an atom? What does it actually look like from the inside? Well, the very first detective to take a guess was a scientist by the name of J.J. Thomson.
Now, Thomson's idea was really simple. He said, just imagine a watermelon. You know, a tarboose. He thought the entire red, juicy part of the watermelon is the positive charge, just spread out everywhere. And the little black seeds stuck inside, those are the negatively charged electrons. A simple idea, no? It was a great first guess, but remember, at this point, it was just an idea. There was no real proof.
But then, beta, the story gets a big, exciting twist. A new scientist, Ernst Rutherford, came along and said, okay, this watermelon idea is nice, but let's test it. And he designed a brilliant experiment that completely changed everything.
So what did he do? Look at this setup. Imagine you have a machine that can shoot tiny, super-duper fast cricket balls. He called these alpha particles. And he aimed them at a sheet of gold foil that was so thin it was almost like a ghost. You could almost see through it. Simple plan, right? Shoot balls at a thin sheet.
Now, you tell me, if the atom is like a soft watermelon, what should happen? All those tiny cricket balls should just zip straight through it, isn't it? Maybe one or two will change path a little bit. That is exactly what they expected. But what they saw, oh my God, it was absolutely shocking.
So here's what happened. Point number one, most of the particles went straight through. Okay, that part was expected. Point number two, a few of them got deflected by small angles. Interesting. But point number three was the shocker. A very tiny number, about 1 in 8,000, hit the foil and bounced straight back. Can you imagine? It was like firing a cannonball at a piece of tissue paper and having the cannonball come right back and hit you. It was unbelievable. And this graph shows the proof. You see, most particles have zero deflection. They went straight. But look at the tail of the graph. A few particles were deflected by huge angles. This was the clue. It meant that the watermelon idea was wrong. There had to be something very small, very dense, and very powerful hidden inside the atom.
This shocking result led Rutherford to a mind-blowing conclusion. He said, the atom is mostly empty space, 99.9% empty. All the positive charge and almost all the mass is packed into an unbelievably tiny spot in the center, which he called the nucleus. And the electrons, they are flying around this nucleus, just like our planets go around the sun.
And when I say tiny, I really mean it. The atom is about 100,000 times bigger than its nucleus. To give you an idea, if the nucleus was a cricket ball placed at the center of a huge cricket stadium, the electrons would be like tiny specks of dust flying around in the outermost seats. The rest of the stadium, completely empty.
So everyone was happy. Mystery solved. We have a beautiful solar system model of the atom. But not so fast. There was a huge, fatal flaw in this model, a problem that nobody could solve.
You see, according to the old rules of physics, what we call classical physics, any charged particle that is moving in a circle must lose energy by giving off radiation. So this poor electron, as it orbits, should be losing energy continuously. It should spiral inwards and, in a fraction of a second, poof, crash into the nucleus. But do atoms do that? No. You are made of stable atoms. I am made of stable atoms. So the model had a serious problem.
So to summarize, Rutherford's beautiful model failed on two big counts. First, it could not explain why atoms are stable. Why don't they just collapse? And second, it couldn't explain something called line spectra. You see, every element, when you heat it up, gives off light of very specific colors, like a unique barcode. Rutherford's model had no explanation for this.
So the mystery got even deeper, and just when everyone was stuck, a new hero entered the story. A brilliant physicist named Niels Bohr. He came and said something radical. He said, maybe the old rules of physics don't work inside an atom. We need new rules. So Bohr proposed 3 new magic rules for the atomic world. Rule number 1. He said electrons are not allowed to be anywhere they want. They can only exist in special, stable orbits where they don't lose any energy. Think of them like special lanes on a highway where you don't need any petrol. Rule 2, these orbits have a fixed amount of angular momentum. And rule number 3, the most exciting one. An electron can jump from a high-energy orbit to a low-energy orbit, and when it jumps down, it releases a packet of light energy called a photon.
These new rules gave us a completely new way of looking at the atom. It's not a solar system anymore. A much better way to think about it is like a staircase.
That's right, a staircase for energy. An electron can be on the first step, or the second step, or the third step, but it can never, ever be found floating in between the steps. The lowest possible step, which we call n equals 1, is the most stable and is called the ground state.
And these steps have specific energy values. For the hydrogen atom, the ground state, that bottommost step, has an energy of minus 13.6 electron volts. Don't worry, an electron volt is just a very, very tiny unit of energy that we use for atoms. This also means if you want to kick the electron out of the atom completely, you need to give it 13.6 eV of energy. We call this the ionization energy.
And here is the truly beautiful part, Beta. When an electron jumps down from a higher step, let's say step 3, to a lower one, like step 2, it has to release the extra energy. It does this by spitting out a photon of light. And since the energy gap between the steps is fixed, the energy of the photon is also fixed. And a fixed energy means a fixed, specific color. This perfectly explains the mystery of the line spectra. So, mystery solved.
Okay, enough of the story. Now for the most important part, the part that will get you marks in your exam. So full concentration now. Let's do a quick revision and then solve a problem. Just remember this one small table. It has everything you need. Thomson gave us the watermelon, Rutherford gave us the tiny nucleus in the center like a planet, and Bohr gave us the quantum model with fixed energy levels and electron jumps. See? Watermelon, planetary, quantum. Simple. Now let's see what a question from your exam paper might actually look like. We will take one straight from your textbook, example 12.3, so you can see it's not scary at all.
Okay, here's the problem. It says it takes 13.6 eV of energy to separate a hydrogen atom. Compute the orbital radius and velocity of the electron. Now, don't get scared by the words. The total energy is given, and we know that total energy is just the negative of the kinetic energy. From kinetic energy, you can find velocity. Once you have velocity, you can use the formula for centripetal force to find the radius. Go on, pause and try it yourself. The full solved example is right there in your book for you to check.
See? I told you it was simple. Once you understand the story, the problems become easy. Just go through this one more time, and I'm absolutely sure you are going to get full marks in this chapter. I have full faith in you. All the best, beta. But before you go, let me leave you with a little thought. Everything we talked about, Bohr's model, works perfectly for hydrogen, which has just one electron. But what happens in atoms with more than one electron, like helium with 2 or oxygen with 8? Well, that is a much, much more complex and exciting mystery. And that, my dear children, is a story for another day.